This is part 2 of the lecture on the spherical Earth. In part 1 of this lecture, I went through the observational evidence that we have that in fact the Earth is not flat. So the observational facts that were depicted in part 1 of this lecture definitively prove that the Earth is spherical. So now that we know that the Earth is spherical, the next most obvious question becomes the following. If it's spherical, this then means that it is of finite size, so then therefore, how large is the Earth? Well, the first person to definitively answer this question lived at the time of the ancient Greek civilization that started to flourish a few centuries BC. Specifically, this man's name was Eratosthenes, and he lived in northern Africa. He lived around 240 BC. We know a few things about Eratosthenes today. For example, he was a librarian at the Library of Alexandria in northern Egypt. The Library of Alexandria is essentially the world's first university. He is most famously known, however, for the following measurement. Eratosthenes was able to measure accurately the size of the Earth using nothing more than a stick and a length of rope. Now, in order to understand Eratosthenes' measurement, we have to first of all go through a little bit of mathematical background. All right, so first of all, everybody knows the answer to this question. How many degrees are there in a circle? There are 360 degrees in a circle. But why? Why are there 360 degrees in a circle? Well, the reason why there are 360 degrees in a circle is because that number roughly corresponds to 365 days in a year. However, that number, 365, is a little bit difficult to work with mathematically, so then therefore we have merely rounded it down to something that's easier to handle mathematically, and that's 360. The reason why there are 360 degrees in a circle, quite frankly, is that it's just purely an arbitrary human invention. Instead, however, mathematically, there is a much more accurate way of describing angles, and this is what is meant by a radian. So let me briefly, once again, review with you Radian Measure. Hopefully you are already familiar with radians from mathematics class, but just in case you've forgotten, here's a little bit of a refresher. Okay, let me begin by just simply drawing a circle. All right, so right here is a circle. I'm going to go ahead and draw two radii. There's a radius here, and there's a radius here. And when I draw these two radii in this manner, I create or subtend, as we say, an angle between them. That is like so. Let me go ahead and label this angle here as theta. Okay, now the two radii that I have drawn intersect the circle at the following 2 points, here and here. There is a distance, therefore, that is created on the circle in this manner like so. This distance here is referred to as S, and it's sometimes called an arc length. Okay, now let's say that I draw the diagram roughly as I've done here, such that S and R are the same thing. So imagine that R, the radius here is 10 centimeters for the sake of argument, and the distance S here is also 10 centimeters. If that's the case, if S is equal to R, then the angle theta is described as 1 radian. Let's say, however, that I redraw the diagram. I'm not going to do so, but let's say that I redraw the diagram such that the distance S is twice the radius. If the distance S is twice the radius, then the angle theta is bigger. It's specifically 2 times bigger. In other words, the angle theta is equal to 2 radians. All that's simply being described here is a ratio. That ratio, describing the angle in terms of radians, is as follows. The angle theta is equal to the arc length divided by the radius. Notice how this ratio works for my two simple examples. So in the first example, S and R are the same thing, so they just cancel each other out, and then therefore the ratio is just equal to 1. And we refer to this as 1 radian. In my second example, the arc length S is twice the radius, so then therefore 2R divided by R is equal to 2, and then therefore we simply refer to that ratio as 2 radians, and so on and so on. Notice that this ratio here has no units associated with it. You have a distance divided by a distance here, which cancels out, and then therefore you end up with what is called a dimensionless quantity. So the word radian is not a unit of measurement. Instead, it is just a name that is given to this ratio. Once again, I hope that this here is a review for you, but let's go ahead and continue that review by asking the following question. How many radians are there in a circle? Immediately, hopefully, you're saying to yourself that there are 2 pi radians in a circle. Okay, well, why is that? Well, in order to understand why there are 2 pi radians in a circle, you have to first of all recall what the letter pi, or the number pi, refers to. Okay, let me begin by drawing a circle here, like so, and then right here is the radius. And let's say that we go all the way around the circle like so, such that we then describe the circumference C. What is it about any circle, regardless of its size, that gives us this number pi? Well, regardless of the size of the circle, if you take the circumference of the circle and you divide it by its diameter, you always end up with the same number, 3.14159 blah, 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 and we just simply refer to that number as pi. It's one of nature's fundamental constants. It literally describes how the universe is flat. Okay, notice how I'm writing this ratio here. Once again, regardless of the size of the circle, whenever you take the circumference of the circle and divide it by its diameter, you always get the same number. You always get pi, 3.14159, etc., etc. Now, notice that this description of pi here is starting to look pretty similar to this basic description here of an angle theta when it is measured in terms of radians. How do I relate the two to each other? Well, once again, refer to this circle here, and then as I said a few minutes ago, let's say that we go all the way around the circle like so, such that I then subtend the angle theta on this diagram in this manner. Using this description here of the angle in radians, let me go ahead and write out what this angle is equal to. This angle theta is equal to the arc length, which is just the circumference of the circle, divided by the radius. Notice that this expression here looks very similar to this expression here. In fact, I can show how the expressions are similar to each other by taking the 2 here in this description of pi and then moving it up to the left-hand side of the expression. When I do, I end up with this. Like so, which is the same thing as this ratio here. So then therefore the angle theta, when you go all the way around the circle, is equal to 2 pi radians. So therefore, the angle theta is 2 pi. Whenever you see this symbol, 3 dots drawn in this manner, it's mathematical shortcut, or mathematical notation, if you will, for therefore. So when you go all the way around the circle, the number of radians is equal to 2 pi. 2 times 3.14 is a little bit less than 6.3. So there are a little bit less than 6.3 radians when going all the way around the circle. Notice, therefore, that 2 pi radians is equal to 360 degrees. This then provides for us a conversion factor to go back and forth between an angle measured in terms of radians and in terms of degrees. Before I take you through that process with a couple of simple examples, 1 degree is a lot smaller than 1 radian. There are 360 degrees in the circle, but only 2 pi, a little bit less than 6.3 radians when going all the way around the circle. But suffice it to say, 2 pi radians is equal to 360 degrees. We can use this conversion factor, as I said, as a means of going back and forth between an angle measured in terms of radians and degrees. When we do, however, we do shortcut it a little bit. I'm going to go ahead and divide out a 2 here from both sides of the expression, such that pi radians is equal to 180 degrees. Okay, with a couple of simple examples here, let me show how we use this as a conversion factor. Let me do some erasing to do so. Okay, so you've seen examples like this before in mathematics class when studying, for example, the unit circle. Let's say that I have a couple of simple angles written out in terms of degrees. So 30 degrees, 45 degrees, and 90 degrees. Let me go ahead and convert each of these angles in terms of degrees into radians. In order to do so, I have to multiply by this conversion factor. Specifically, we multiply by pi radians per 180 degrees. Like so. And now let me go ahead and perform this mathematical example here for these three situations that I've depicted. For example, in 30, this goes into 180 degrees 6 times. So then therefore we simply write the angle here as pi over 6 radians and we just leave it at that. For the second example here, 45 degrees goes into 184 times. So then therefore this is equal to pi over 4 radians. And then lastly, 90 degrees goes into 180 twice. So then therefore this is equal to pi over 2 radians. More times than not, especially when dealing with simple angles associated with the unit circle that you would study in math class, more times than not, we usually leave an angle written in terms of radians as a fraction or a multiple of pi. Now, of course, we can go backwards. That is, we can take an angle that is written in terms of radians and then ultimately convert it back into degrees. So let me choose a couple of examples for that to illustrate. Let's say pi over 3. Let's say pi over 6. And then let me pick something else as well. Let's say 5 pi over 3. I'm going to go ahead and convert each of these simple examples here from radians into degrees. In order to do so, we have to multiply by the following. 180 degrees divided by pi radians. Like so. And now we just go ahead and simplify. When I simplify, notice immediately that the pi cancels out like so. This illustrates the advantage sometimes of writing an angle in terms of radians as a fraction or multiple of pi, because when you convert it back into degrees, immediately the pi just cancels out. And then in my first example here, 3 goes into 180 60 times. So then therefore, this is equal to 60 degrees. And then in my second example here, the pi cancels out like so. 6 goes into 180 30 times like so. So then therefore the angle is equal to 30 degrees. And then in my last example here, let's go ahead and cancel out a pi like so. 3 goes into 180 60 times, and then therefore 5 times 60 is equal to 300 degrees like so. So by using this conversion factor, pi radians is equal to 180 degrees, we can easily go back and forth between an angle measured in terms of radians and in terms of degrees. Okay, now getting back to Eratosthenes. Let me go ahead and do some erasing here. Okay, now as I described earlier, Eratosthenes lived in Alexandria, which is in northern Egypt. Now, due south of Alexandria, in southern Egypt, there was a town at the time that was referred to as Syene. Syene is still there today. Today is referred to as Aswan, Egypt. Okay, on business, Eratosthenes periodically went back and forth between the two towns. So we have Alexandria, and we have Syene. Now, on a very specific day of the year, when viewed from Syene, Eratosthenes noticed something about the position of the sun in the sky at noon. On June 21st at noon, as seen from Syene, the sun is straight overhead. In other words, it's at the zenith. However, due north in Alexandria, if you looked at the sun at the exact same time, that is, at noon on June 21st, would you still see the sun at the zenith? No, it's going to be a little bit to the south of the zenith. So then therefore, this observational fact allows us to make a couple of simple measurements and then therefore calculate the size of the Earth. Here is then a diagram associated with Eratosthenes' calculation. Okay, here's the Earth like so, and then let me draw in the following lines. Like so, where we have way over here off to the right-hand side the sun. Okay, the sun is not infinitely far away. It is a finite distance from the Earth, but for all practical purposes, for purposes of this calculation, just picture the sun very simply as being infinitely far away. This then means that the sun's rays, like so, are all parallel to each other. Okay, and then we're depicting the situation here at noon on June 21st. And then right here is Syene. So if you're standing in Syene at noon on June 21st, you're going to look straight up at the zenith like so, and then you're going to see the sun. However, over here, this right here is Alexandria, further to the north. The dotted line that I just drew here is pointing towards the zenith when seen from Alexandria. Notice that the sun, instead, is way off to the side. The sun's rays form an angle on this diagram like so with respect to the direction towards the zenith as seen from Alexandria. Let's go ahead and label that angle as theta. That angle theta is the same as this angle here. The reason why is because these two lines here and here are parallel to each other. And now on this diagram, what I've constructed here are two radii. There's a radius here, and there's a radius here. And then the distance between Alexandria and Syene, like so. This distance here on my diagram, this distance right here is an arc length. That distance is s. So then therefore, from the description of radian measure, the angle theta is equal to s over r. If you could somehow measure the angle theta, and you could somehow measure the distance between Alexandria and Syene, the only unknown that is left in this calculation is the radius of the Earth. And now we get to Eratosthenes' measurements. Okay, first of all, we have the angle theta on the diagram above. This is where the stick comes into play. In order to measure the angle theta, what you do is you take a stick, and you're standing in Alexandria when you do, and you plant it vertically in the ground like so. It points towards the zenith. And then the sun's rays are coming in on a slight angle like so, which then causes the stick to cast a shadow. The situation then looks like this. Okay, so now we're in Alexandria. This right here is just the ground. And then like so, here's your stick. Okay, and then this direction right here, this is then pointing towards the zenith. So this dotted line that I just drew right here is off in this direction on the main diagram above. And then we have the sun's rays coming in on an angle. Let me go ahead and draw the sun's rays, for example, like so. And then right here on the diagram, this angle here is the same angle theta as the diagram above. Once again, the sun's rays I've drawn here in red now are causing the stick to cast a shadow. If you use a little bit of elementary geometry, this angle here is the same thing as this angle here. And then in order to find the angle theta, all that we're going to do is make two simple measurements. You're going to first of all measure the height of your stick. Presumably you know what the length of your stick is. Let me go ahead and refer to this as A. And then right here is the shadow that is cast by the stick on the ground. Let me go ahead and refer to this distance here as O. You measure that distance O. Okay, and then using a little bit of elementary trigonometry from SOHCAHTOA, let's just now go ahead and use a little bit of tangent in order to find the angle theta. So notice that the tangent of the angle theta is equal to the opposite side of the right triangle that I've drawn here divided by the adjacent side. Obviously, I relabeled O and A for this reason, using the language of SOHCAHTOA to now find the angle theta. So by measuring the tangent of this angle as the ratio, O divided by A, Eratosthenes measures the angle to be about 7.2 degrees. As measured by Eratosthenes. Frankly, this was the easy measurement to make. And then we've got the hard measurement to make. The hard measurement to make is the distance S on the diagram above. You have to measure the distance from Alexandria to Syene. Now, Eratosthenes himself probably didn't make the actual measurement. He hired professional surveyors to do so, people that would actually make very accurate measurements as best they could by walking large distances. So those surveyors had to basically do the following. Imagine that this, for example, is the length of rope. And then what they had to do was they had to start in Alexandria and then they walked. They walked from Alexandria to Syene. And as they did, they basically took the length of rope and they did this. 1, 2, 3, and so on. Ultimately, it probably took them several weeks to make the measurement from Alexandria to Syene. In terms of modern units, the distance from Alexandria to Syene is 800 kilometers. So it's not a trivial distance, that's several hundred miles. So Eratosthenes measures S to be equal to 800 kilometers. Once again, he hired professional surveyors to make that measurement. Okay, now that I have the distance S and we have the angle theta, then we can use the ratio above to find the radius of the Earth. Before we do so, however, we do have to convert the angle theta of 7.2 degrees into radians. So let me go ahead and do that for us here. Okay, so the angle theta is 7.2 degrees, and then we multiply by pi over 180 using my conversion factor. I'll just do this on my calculator, and I'll write out the angle here in radians as a decimal. That's fine. So 7.2 times pi over 180. Okay, going out a couple of decimal spaces, this is about 0.1257 about. Radians like so. Okay, and then we have the distance S from earlier to be 800 kilometers. Using the ratio above, let's go ahead and cross multiply now and solve for the radius of the Earth. So the radius of the Earth then is equal to S over theta. This is 800 kilometers, and then divided by 0.1257 about radians. Once again, recall that a radian is just a name that's given to the ratio. It's not a unit of measurement. So the units that I will end up with here for the distance R is in fact in terms of kilometers. So 800 divided by the angle in terms of radians, and this works out to be about 66 kilometers, like so. Now, how does Eratosthenes' measurement compare with the actual value? Well, as the Earth rotates, as I mentioned in part 1 of this lecture, it bulges a little bit at the equator. However, the Earth's mean radius is 6378 kilometers. So compare the two. We know this number today to a high degree of accuracy. This is what Eratosthenes measured more than 2,000 years ago. He was off by only a couple of kilometers. Eratosthenes will be remembered forever for this calculation. And the reason why is because his calculation is elegant. A solution in physics and in science in general is considered to be elegant for the following reason. Take a seemingly extremely difficult problem. Ask a person who lived more than 2,000 years ago to measure the size of the Earth. There's basically no technology at the time. How do you make such a measurement? Eratosthenes recognizes that the problem is actually nothing more than a geometrical problem, and ultimately if you make a couple of simple measurements that were possible at the time, you can then easily determine the size of the Earth. Okay, that concludes part 2 of this lecture.